Hello and welcome back. In this video we'll be going over section 5.1, jointly distributed random variables, but in this case our random variables are continuous. So let capital X and capital Y be continuous random variables. Then we begin with the following definition: the joint probability density function, or for short joint PDF, of capital X and capital Y is a function little f of x comma y such that we have the following. For any region A that sits in R2, probability that the ordered pair of random variables, capital X and capital Y, are in that region A is equal to the integral of little f over the region A. So, and this is true for any region A sitting in R2. And the way to think about this is that A can be such a region. It doesn't have to be a rectangle or anything of the sort, just a region that can be integrated over. So in particular, when A is this rectangular region, the probability that our ordered pair of random variables, capital X, capital Y, is an element of that region is the probability that the first component, capital X, falls on the interval from A to B, and the second component, Y, falls on the interval from C to D. Well, this is an integral over a rectangular region, which can be broken into the following. The following integral, where we have definite bounds for both integrals. And so the idea here to view this is that in this particular case, it's nice to draw a picture to this, is that on the right here we can imagine A as being this region. So it's this rectangular region in the xy plane. Is a scalar function, and the corresponding probability of this event, so the probability that capital X, capital Y is an element of A, is the volume underneath this portion of the sheet. So a couple properties is that one, f of xy is always greater than or equal to 0, and this is for every ordered pair, little x, little y, in the real plane. And number two, if we compute or integrate, add up all the area underneath this scalar function, so over the entire plane R2, this needs to be equal to 1. So these two properties are the continuous analog of the discrete, which was mentioned in the last video. So just like the discrete case, we have what are called the marginal probability density functions, or for short, the marginal PDFs of capital X and capital Y. And this is given by the following. little f sub capital X of x is defined as following. So f sub capital X is the PDF of just the random variable capital X, but it's derived from the joint probability density function of both x and y. So in this sense, you can imagine that the PDF of just x can be extracted from the joint PDF of x and y. And it's defined as follows. So this is an integral. And even though y's show up, remember that we're integrating, so this is a definite integral with respect to y. So in the end, this will only be a function of x. In other words, y is a dummy variable, or variable of integration. Similarly, the marginal PDF of capital Y, denoted by the following, is given by this expression. So the marginal PDF is just the x and the y swap roles. So this is an expression where we have two variables, but we integrate with respect to x, resulting in a function of only y. So to see that these are in fact the PDFs of capital X and the PDF of y respectively, we can look at the following. We can notice that for any interval AB, the probability that capital X falls on the closed interval from A to B is the probability of that same event and the random variable capital Y falls on the interval from negative infinity to infinity. So to see that this is true, that these two are actually the same event, we can identify this inequality as an event E. In other words, this corresponds to all the outcomes of our sample space in which the random variable capital X results in a value that falls on this interval from A to B. So this is denoted by E, all such outcomes. Well, this is that same subset, or that same event, E, and we're conditioning on, or I'm sorry, not conditioning, but also requiring that capital Y falls on the real number line. Well, since capital Y is a function to the real numbers, every outcome in S is going to fall on this real number line. So this identifies with the event capital X. And so remember, the comma means and, so this can be interpreted as intersection. And we can see that these two things are true. E is equal to E intersect S for every subset of the sample space capital S. So by definition, this is the integral over such a region in R2. So where X, so this is a rectangular region, where X goes from A to B, and Y goes from negative infinity to infinity. Of f of x comma y dy dx. And the way to think about this is that if there's my y-axis and this is my x-axis, then we integrate over the following region. Okay, so it's this rectangular region, and it extends on for infinity in the vertical directions, and that's what we're integrating over. So that's what's defined by this event here. And I suppose these should really be solid lines. Doesn't matter because we're dealing with continuous random variables, but we are including the boundaries. It's less than or equal to symbols. And so what is this equal to? Now remember, when we're able to express things as double integrals, you can think of doing the inside integral first. So this inside here is an expression of x. So after you integrate with respect to y, this gives back an expression of x. Or in other words, the integral from a to b of the marginal PDF of capital X. So in other words, this marginal PDF is in fact the PDF for the variable capital X, and it's derived from the joint PDF of capital X and capital Y.